Ladies and gentlemen, I'm sorry for a couple of minutes late because I actually have been speaking for a couple of minutes, but I've just been informed by Roger Anderson that it wasn't live. And thank you very much. I thought he was being rude, interrupting me, but thank you very much. I was just talking to myself. So I'll repeat what I said. Thank you, Roger. Today, we are delighted to have Professor Halim Boutayeb from the University of Quebec in Canada. Now, those of you who have been keeping an eye on the questions and the discussion and so on will know that Halim, okay, yeah, I'm just looking at your live. That's great. That Halim has been participating in recent months in our conferences and making some very appropriate comments and questions and so on. And I've had a very brief look at what he's been doing. Obviously, he's a theoretician. He's done some very significant work. He's just informed me, actually, that he's giving a paper to some conference next year in Dublin. He's asking me, am I there? Yes, so I'd like to meet him, actually. But so the work, as far as I could say, or if I could be bold enough to make a very brief comment, is of very great substance. It's very theoretical and very logical, and yet it's not in your face. He's bringing people around to looking at his ideas, which, you know, on the face of it would be like a red rag to a bull to a lot of the organized or mainstream academics who sort of shy away from any question at all of Einstein's 1905 paper. So what Halim is talking about today, he proposed an origin and thorough analysis, he says, of the behavior of electromagnetic waves in the presence of moving bodies. So this is all familiar terminology, but he's using the finite difference time domain, FDTD method, theoretical method. So I just read out the spiel he's given me. So and I put this up on the notice, of course. The analysis of electromagnetic problems with moving objects has many applications: RF, radio frequency, Doppler radars, astrophysics, GPS, electromagnetic gyroscopes, etc., etc. This seminar proposes an original and thorough analysis of the behavior of electromagnetic waves in the presence of moving bodies by using the finite difference time domain method. So I'm certainly extremely interested in his analysis of this theoretical basis, but I'm not quite sure what he's going to show by using the FDTD method. So I'll be all ears on that. And as usual, we'll restrict ourselves. I see the questions are coming in already. So we'll restrict ourselves to giving Halim sort of like roughly an hour to present his information. I know he has some PowerPoint slides as well, which I dare say will help us. And I would say, please don't be frightened if he has some theoretical matter there which you're not familiar with. I mean, this is very detailed, and I'm sure in the discussion, if you want to raise any of the points or even ask him elementary questions, I don't know what you mean by that symbol, he'll be very happy to come back and enlighten us all on that. And then I see some people are coming into the green room now, so hopefully we'll have a nice discussion. Yeah, I see we have a couple of people come in. So okay. As usual, I'm Ian Cowan. You know that I'm hosting today's meeting. I'm delighted that we've had Halim, because I've only noticed in recent months Halim has come in, and I think actually it's probably not least due to Roger Anderson's videos on the subject, you know, which sometimes are quite conversational, but I think they have attracted a number of people, including Halim, if I may say so. So without further ado, I'm going to give him the floor. I'll bring him up just before I disappear. There you are. Good day, Halim. I think I can say good. No. You're also in the morning. Yes,
I'm in the morning. Yeah.
I say good day. Yeah, your morning.
Yeah. Hello. Good morning, everyone, and good evening. Should I start?
So, shall I just give you the complete floor, or would you like to put your slides up? Would you like a couple of minutes
Yeah,
just your own photograph, or shall I put the lot up?
I will just talk before. So just say thank you, Ian, for the invitation.
Let me give you the complete floor, Halim, and just tell me when you want me to put up your slides. So okay. I'll disappear now for the moment.
So hello, everyone. Good evening, good morning, depending where you are located. And I want to thank Ian for the invitation and all the members of the CNPS. So today I will talk about a really interesting subject, and I hope it will be interesting for you too. So please, you can let me share the screen. Yeah. Can you see my screen?
Yes, it's perfect. Okay. I can see it. Yes, thank you.
So the title is Computational Electromagnetism with Moving Matter and Some Quantum Phenomena. I would like to dedicate this presentation in the memory of Wolfgang Engelhardt. I had the pleasure to have a discussion with him and participating in different tweets in ResearchGate between 2016 and 2019. And we talk about classical electromagnetism and also about the special theory of relativity and the theory of relativity in general. I work in Gatineau. Gatineau is a French-speaking part of the capital region of Canada. So you can see here Gatineau and Ottawa is the English part. I live in Ottawa, but my university is located in Gatineau. So for today, this presentation actually is part of a work that I usually present, but usually there are more technical parts that I have removed, and I added some other parts which are more general and more for hopefully for a wider audience. So this is the outline, as you can see. So we can say what you see in the left from point 1 to point 10, it's more about philosophy and general theory about electromagnetism and physics. So let's start with this one. Equations have a context in physics. When you write an equation, you have a context in mind. You don't write it without a context. For example, let's see I observe the height of a building that is under construction. And I see that there is every day the height is increasing by a certain amount. And this is a regular increasing of the height of the building. And let's say I want to write an equation. And I will write h is the height of the building. For example, let's say in meters. H naught, maybe this is the height in the beginning when I start to see how the height is changing. And alpha is, for example, expressed in meters per day. And t is time, for example, expressed in day. So this is, I just wrote an equation to express what I am seeing, what is my observation of the height of the building. So h equal h naught plus alpha t. So let's take this equation and just reverse this equation and write t equal h minus h naught over alpha. So mathematically, this is correct. I didn't do any mistake. I just took the equation. I just reversed the equation. But now, let's see this equation. This is time equal h. Time is a function of height and a certain coefficient alpha. I cannot take this equation and say that time itself is a function of the height of the building. This makes no sense. Like if the building stop, it means time stop. If the building construction is faster, it means time go faster. No. So there's a context in an equation. Here in this equation, time is an independent variable that is not an output. It is an input of my equation. The output is the height of the building. So let's go now to what we call auxiliary variables. So auxiliary variables are not physical quantities. everybody knows about this experiment that we do in high school about free fall. So we know that the distance of the object falls under a constant acceleration and is given by this equation. So d is a distance, a is acceleration, and t is time. But when we record the results, the data, it is more convenient to record the distance versus this parameter, half of t squared. Why? Because then we can see the slope, and the slope will give us the acceleration, and it will give us actually the gravitational constant g. But this variable, half t squared, I can call it m, I can call it t prime, I can call it x, or I can call it anything I want. I just have to describe that, but it doesn't have a physical meaning. It's not because I use this variable that it has a physical meaning. It's just more convenient to use this variable to analyze the data. So auxiliary variables are not physical quantities. So now let's go to the wave equation. For simplification, we will just look for the one-dimensional wave equation, which we can call also the D'Alembert equation, which is in this form. So you have a second derivative of a function a with the space variable x, and second derivative of the function a with the time variable t. And c here is the speed of propagation. This wave equation is the same, exactly the same wave equation that you will use if it is a sound wave or if it is a light wave. For a light wave, c is the speed of light, and a is a transverse component of the electric or magnetic field. For sound wave, c is the speed of sound, and a is the pressure. Solution of the wave equation are wave functions, and they have this form with the omega here is 2pf, so the f is a frequency, t is time, k is a propagation constant, and x is a space variable. This wave function represents a wave, for example, a sine wave or combination of sine waves, but it doesn't represent a ball or something else. It just represents waves. So now let's talk about the theory of light from Bradley to Lorentz. So Bradley in the 18th century did this analysis about the stellar aberration. Many people know about the stellar aberration. When you look at a certain star, so you imagine that the star is very, very far. So it's so far that the angle, when you look to that star, the angle of the telescope should stay the same angle of the telescope. But it is not the same angle during the year. At different period of the year, you have to change the angle of the telescope to see the same star. Even the star is very, very far. So what's happening here is the effect of a moving observer, and the motion of the observer make this aberration, and we can understand it when we run in a rain like this. The water drops looks like they are dropping with a certain angle. So this is very well known, and this principle, it is the same result either you use a particle theory of light or you use a wave theory of light. It is the same principle. So this is the equation for the stellar aberration, and then in 1810, Arago was working on the particle theory of light, so the Newton theory of light. And he used a prism, as you can see here. And he expected, when he used the particle theory of light, he expected that the angle of the aberration should change with the refractive index of the prism. But in his observation, he found that there is no change in the aberration. It was always the same aberration, no change. So no function of the index of refraction of the prism. And then Arago asked Fresnel, who was interested with the wave theory of light, and they were inspired by Young experiments, actually. And so he asked Fresnel, can you use a wave theory to explain my results? And so wave theory of light means there is a medium, and the medium here we call ether. So Fresnel found that if when the medium with the refractive index n move with a certain velocity v, if the ether move with this velocity, so with this coefficient, this coefficient, the Fresnel drag coefficient, so instead, the ether doesn't move totally, but move with this coefficient, and n is the refractive index of the medium, then he will cancel the effect that Arago wanted to measure. So he got this equation. So in the medium that is moving with the velocity v, the speed of propagation will be of the wave will be that form. Then in 1851, Fizeau, another French scientist, did this experiment with the moving water, where he analyzed the speed of propagation of light in the moving water. And he found that it is in agreement with what Fresnel got, that the speed of propagation looks like is modified by the motion of the water, and looks like similar to this equation. So at that time, this equation, or the Fresnel drag, was very famous, but there was some debate about physical meaning. Is this really the medium moving? Like Stokes thinks that medium is not moving, because if it is moving and the refractive index is a function, for example, of frequency, how can a different frequency the medium move a different velocity, for example? So that was not, the equation was accepted, but the meaning or the physical, the interpretation of the equation was still in debate. So I passed many work before, but Maxwell, based on Faraday, Ampere's, Gauss work, developed his electromagnetic theory, and everybody knows Maxwell's equation. And Maxwell equation in a region with no charge and no current can be working like this and give you a wave equation that we see here, the same wave equation I presented before. So this theory shows that the electric, in the wave propagating here, electric field and magnetic field are orthogonal, and they propagate and they are orthogonal to the direction of propagation. Then this paper is very, very important, is 1887. Voigt was working on the wave equation, and he specifically say in the paper that this is wave equation, the same wave equation we use in sound wave or light wave. And as you can see here, in elastic incompressible medium. So let's see for one dimension. So what Voigt wanted to do is he wanted to analyze, to reanalyze the Doppler effect by using the wave equation. Let's start with a 1D problem. So with the wave equation, if the observer is moving with a certain velocity v, will be modified, will be changed to this equation that you see here. You can see now the equation is more complex. You have the v square, the minus 2v here. The equation is more complex. That's only 1D, and the 2D problem also will have something similar. So he wants to analyze this equation, but it will be easier if he has this kind of equation. Why? Because this equation, this partial differential equation of second order, has simple solution like this ones. And then he will be able to reanalyze the Doppler effect by doing that. So he said, I want to change the form of this equation to this equation, which is the wave equation with the observer not moving. And then he need to add auxiliary variables that you see here. So let's come back here. What do we say about auxiliary variables? They have no meaning. They are just help to complete the analysis. Let's take some time with these two equations. In Voigt works, this equation here and this set of equations are the same. You don't have to do this transformation. You do it because this equation here is easier to analyze. And that's what Lorentz will use actually. So in Voigt's work, they are the same. You can either work with this if you can do it, or if you cannot, you can work with this. Actually, today's, you could resolve this one numerically. You don't need to do a transformation. You don't need to change the variables. You don't need to use this auxiliary variables. You could resolve this equation here. Okay, so that's very important. And in 3D, the auxiliary variables used by Voigt will be this shape. And you can see now you have y prime, z prime, t prime, and x prime. And you have here the gamma factor, which is writing here. And then he has a wave equation, which is the 3D wave equation when the observer is not moving. Now there is a problem here. If you look here, there is a certain wave propagating, for example, solution of the solution, and the observer is moving. What is the speed, the relative speed between the observer and the wavefront? It will be c plus v or c minus v, based on, this is easy to understand, and you can find it with this. But now if you change here, and you decide to say that x prime is real space and t prime is real time, then c is the speed of propagation. So something wrong. You cannot interpret that as a real wave equation. You have changed the shape. This one was the real one. This one is correct if you understand that t prime is not time. Okay. Then you have Lorentz, who worked from 1892 to 1904 on electromagnetic theory when you have an object in motion. Yeah. And Lorentz adopted Voigt auxiliary variables. And he multiplied them later with a gamma factor. So in the beginning, in the first papers here, he didn't multiply, but after that, he multiplied with a gamma factor. So you have from 1892 to 1904. So let's look to this one. You can see here how he used the Voigt idea of the auxiliary variables. In that paper, Attempt of a Theory of Electrical and Optical Phenomena in Moving Bodies, 1894-5, we will see how we can get this transformation. He called that Lorentz theorem of corresponding states. He has, when you have an observer in motion, he has to change the electric field and the magnetic field. But you can see here the T prime and R prime are exactly the same as Voigt. That's exactly the same as Voigt. He didn't multiply yet with the gamma. And then he used the solution that we have for the wave equation with no motion, with no observer in motion. So this is f omega t prime minus x prime. He just used t prime x prime. When he replaces, he can replicate the Doppler shift, for example. He can replicate the stellar aberration, or he can replicate the Fizeau experiment with using this trick or this technique, and at that time, especially when he proved that he can replicate Fresnel formula, his work became very famous. And at that time, there was not sure if they have to follow Maxwell's electrodynamics or Weber's one or other ones. And this actually was a great support of Maxwell's electrodynamics. In 1904, he used again Voigt's auxiliary variables, but he multiplied them with a gamma factor, as you see here. And that's now the new equation that he will use. So he explained that the gamma factor will explain the length protraction hypothesis to explain the Michelson-Morley experiment, and also the increase of mass in the Kaufman experiment or particle accelerators. So now let's talk about Einstein 1905 Special Theory of Relativity paper. The title of the paper is On the Electrodynamics of Moving Bodies. So electrodynamics is more about Ampere's, Weber's work about moving charges. But mostly in his paper, he talked about Maxwell's equation. So we could call it electromagnetism. So electromagnetism in the presence of moving objects. Okay. What is the main idea or contribution of the paper? The main idea is that Einstein gives a physical meaning to Voigt's auxiliary variables in part 1 of the paper. But this interpretation is not needed and it's out of context. The work was not about time, was not about this interpretation that he gave. In the introduction, the principle of relativity is not a clear concept. In 1894, Heaviside uses this term relativity, but he refers to the fact that motion is relative. Motion is relative. Everyone can understand that. There's no problem with that motion is relative. The postulate about the speed of light independent of the speed of the source, that is true for the wave theory. But when he used Voigt's variable, he implicitly imposed the speed of light to be constant for all observers. Okay. We will see that in the simulation. If you move the source, the speed of propagation doesn't change. So it's okay when you write, you read the postulate, the way the postulate is writing is okay. But what he's doing is different. When he interprets that the change of form of the wave equation that Voigt has used is true, and the speed of propagation is c, when even the observer is moving, then that's different. It's not in agreement with the postulate that he wrote. So later on, to explain the principle of relativity, he associated that with Galileo. But if you look to Galileo's work, there is no transformation in Galileo's paper, and there is nothing related to relativity or something about the concept of relativity in Galileo's work. And Galileo's both experiments, they refers to inertia. It's easy to understand with the principle of inertia. And then there is a question of the existence of ether. In the paper, Einstein said there is no medium, there is no ether. But that's not important for the work he's doing. He relies on Maxwell's equation. He's using the same equation Lorentz is using. And in Lorentz's work, there is ether. So the work, and also the work Faraday was thinking about no ether, and Maxwell with ether. The Maxwell equation are on the same electric and magnetic field work done by Faraday and Maxwell. And in part two, he repeats mainly the results that are obtained by Lorentz for the transformed electric and magnetic field and for the accelerated electron, including the mass increases formulas. In part two, Einstein also derived new formulas for the Doppler effects, for the moving observer and moving reflector. So there is no moving source there, but in 1907, he has another Doppler effect formula for the moving observer. And also for the stellar aberration and the amplitude and energy of light with a moving reflector or moving observer. So for the last one here, we will compare with the result that we have with using numerical techniques. So now let's talk about Lorentz transformations. So Lorentz transformation, as I said, these are Voigt's variables multiplied with the gamma factor. There's one here. Who called them Lorentz transformation? Poincaré named them Lorentz transformation. Poincaré is a mathematician. He was a mathematician expert in mathematical transformation of the complex plane. So he used this term transformation in his work. He called it Lorentz transformation. But is it really Lorentz who invented that? This is not from Lorentz. In a book and in a letter to Voigt, Lorentz admitted that the inventor is Voigt. As you can see here, in this two, this is from the book, and this is from a letter he wrote to Voigt. So it's not from Lorentz. And if we study Poincaré career in mathematics, it is possible to find other times where Poincaré named a mathematical tool with someone that is not the inventor. For example, he named Fuchsian groups, groups that he invented. He is inventor, but he called them Fuchsian groups. They are not transformation. What does it mean, transformation? What does this is T prime, X prime, Y prime, Z prime? What does that mean, transformation here? So as I said, Poincaré was working in mathematical transformation of complex plane. If you study this mathematical domain, it's easy to understand. You have a certain complex plane, you transform Z to Z square, something like that, and you have some, so there is no problem of calling them transformation. But now when you call the variables that Lorentz and Voigt were using transformation, there is something you add something. Do you mean there is physical transformation? Is this something new? What's this? So Lorentz didn't call them like this. He called them auxiliary variables. So the utilization of the term transformation is misleading and could mean that there is new physical phenomena, but there is not. It was just a change of variables, but today, instead of using this change of variables, we could resolve the equations numerically without doing a change of variable. Now let's compare Lorentz and Einstein. So Lorentz, his theory is ether theory. So Lorentz ether theory, and Einstein is special theory of relativity. So if you look in the literature, generally they say that they are both considered equal, and they say that they prefer STR because it's simple and it doesn't have the concept of the ether. But the problem is explanation of a Sonic effect within STR is subject to debates. So in Lorentz theory, space is absolute, time is absolute, and speed of light is relative. So something really easy to understand. But here in special relativity, space is relative, time is relative, and speed of light is absolute. And Voigt-Lorentz auxiliary variables, in Lorentz theory, they are not fundamental except the length contraction. It's only the length contraction, when he multiplied with the gamma factor, the length contraction is the physical effect that he added. But this is an hypothesis. It doesn't have to be necessarily true. So except for that, the variables that he used are not fundamental. You don't have to use them. But in the special theory relativity, you have to do this change of variable. You have to do this transformation. Now the question about how you can apply the Lorentz ether theory or special theory of relativity in computational electromagnetics with moving objects. It is simple within Lorentz ether theory if you neglect length contraction. If you remove length contraction, then it is easier to do that. You just don't use the variables. You just resolve Maxwell equation numerically. If you want to do it in special theory of relativity, it's complex, and I will say it's impossible. How can you move object with any motion, any complex motion? So as we say here, we prefer Lorentz ether theory, and we don't consider length contraction. Here, I want to present different passes of electromagnetic theory. So we have the works of Ampere, Gauss, Faraday, and then there is a Maxwell contribution. So Maxwell's equation, and Maxwell actually was praising Weber work, which is Weber electrodynamics, which is a different theory for electrodynamics. And Maxwell, in his book, he said this is a different approach, which is also valuable. And if you compare to Maxwell theory and Lorentz force, this theory satisfies Newton's third law, but not Lorentz force. So this is a possible path too. We could continue, or maybe we can merge them. There is Ritz who also work on that, Assis, and today we have Stephen Kuhn. He's also doing computational electrodynamics, as you can see in this figure here, but based on Weber's electrodynamics. So myself, I'm expert in Maxwell's equation. I work on Maxwell's equation. So here we can say there was two parts up in Maxwell's equation. You have to, when you add motion in Maxwell's equation, you could use Lorentz transformation, and then you have another two parts, STR or Lorentz. STR means you take this transformation as real and the time, etc. But in either path here, you will be in a dead end. Why? Because you cannot apply that to non-information. You cannot apply that to multiple objects in motion. You cannot distinguish the motion of the observer, the source, and the object. You just transform E, H, X, Y, Z, and T to another set of variables, which are function of V, which is a uniform motion. But you don't know what you're doing. Moving observer, what is exactly you doing? But the other path here is to resolve Maxwell's equation numerically without any transformation. In that case, actually, we can combine Lorentz here because we just in your Lorentz construction. So Lorentz is easy to put in this path. But here you cannot because the transformation is necessary in STR. The idea of STR is a transformation, is Lorentz transformation. And if we do that, then we can use that for many practical application. So here I put what Louis Essen said: the teaching of relativity hinders the development of a rational extension of electromagnetic theory. He is true. If you continue here, it's a dead end. You cannot continue more than that. So the theory of relativity. The theory of relativity, I used to think like Rutherford or like Essen, that it is a joke or a swindle. Rutherford, he was awarded the Nobel Prize in chemistry in 1908, and Essen is inventor of the first practical atomic clock. But now I consider the relativity as a blessing, because many scientists have wasted their time of metaphysics. That means it has left a vast, largely untouched branch of science. So there is a niche where we can publish work, valuable work, useful work, if we ignore this theory. I do it because I'm working on electromagnetism. I work on the electromagnetic theory, but I will say that someone else working on astrophysics or another part of physics where relativity is present, I will suggest to ignore this theory and try other paths. Stokes theory. So as I said, we said Lorentz use ether theory, but Lorentz consider that ether is immobile. Okay, because that will be in agreement with the stellar aberration and other physical phenomena. But to explain the Michelson-Morley experiment, he need a lens contraction hypothesis. We still call it hypothesis because it is an hypothesis. Another alternative to that will be that the ether, the medium, is moving with Earth, so attracted by the gravity of Earth, but is not rotating with Earth. And actually, this was Michelson, conclusion in his paper that the ether is not immobile. So within this theory, this will be in agreement with stellar aberration, Michelson-Morley experiment, Michelson-Gale experiment, and the Sagnac effect. So the medium is moving with Earth, but not rotating with Earth. But we could say that we don't have necessary access to the ether or the medium itself. It could be only the electric and magnetic field moving, attracted by gravity, and maybe the ether is still immobile. So we don't know. Actually, the tools we are using is only electric and magnetic fields. So let me continue now to the FDTD method. So the FDTD method, so the algorithm was proposed in 1966. This is about 11 years after Einstein's death. So this tool was not available to Einstein or Voigt or Lorentz. This tool allows to resolve Maxwell's equation numerically in time domain. And even the algorithm was proposed in 1966. It was used the first time for a practical application in 1975. And today, the finite difference time domain method is used for a wide range of application, from RF, microwave, millimeter wave, terahertz, optics, etc. So this is a tool that is used in many commercial software to design antennas, to design components, RF components, circuits, systems, from wireless communication to radars, etc. The FDTD doesn't introduce new physical phenomena or aspect to Maxwell equation, just resolve Maxwell equation, not adding any something physical new, physical effect new. So the principle here, as I say, if you want more details about the FDTD, I have a more technical presentation about this technique in my. You can see that in my YouTube channel. So the principle is to discretize space and time, and to use finite difference. You can decrease the space and the time step as small as possible to reduce the error as small as you want. So here I show in black the Yi algorithm. This is the algorithm how the Yi that Yi used to resolve Maxwell equation in time domain. And in red here I add the implementation of moving bodies in our code. So we did our own codes, and we can move. You can see that we can move many objects. We can move the fields itself, and we can move the object not necessarily at uniform speed. We can move at any speed, at any complex motion. They can oscillate, accelerate, etc. In the simulation, we have to use excitation. So how to choose excitation? The best excitation here is to use a windowed sine. Why? Because of course we cannot send a sine, because sine wave is infinite. So we have to limit that in time. But if you look to the spectrum, so the Fourier transform here, the spectrum, you will see the peak correspond to the frequency that we have chosen here. And this is very helpful for the analysis when we have motion, because when we have motion, we will see that this peak will change. And then we can analyze the Doppler effect. So let's start with the moving observer. Okay, let me stop here. Okay, I will explain here. So there is a plane wave source at this position here. The plane wave source, as you see, will generate the window sine wave on both sides, on this side and this side. This one propagating in x direction, this one in minus x direction. And the red point you see here is the observer. You see the observer is moving towards the wave. Okay. So the observer, this is how we save the fields, and we can plot the signal we receive at the observer point for different velocity of the observer. So the black curve here, the first one is for v equals 0. So v over c equals 0. Then we have v over c equals 0.2. Then we have v over c equals 0.6. So if we analyze this data, it's easy to show that the electric field of when the observer is moving is like the same as electric field when it is not moving. But if we multiply t with this, it's just analyzing the data. But what you see is the Doppler effect. You see, the frequency is changing, the wavelength is changing because of the motion of the observer. And actually, this term here is very similar to what Lorentz called local time. As you see here, you just put x equals ct in this equation, you have the same here. This now, if you analyze how the frequency is changing. You see here, this is for the spectrum. This is in time domain, and this is in frequency domain. If you see how the frequency is changing, you analyze that, you will find that f prime over f equal 1 plus v over c in one direction. In the other direction, it will be 1 minus v over c. That's for different v over c here. And also you can move with a certain angle. If you move a certain angle, you have 1 plus v over c cosinus theta. Theta will be the angle from the motion. This formula here is the same formula we got with the classical wave theory. And here we got it with using Maxwell equation resolved numerically. When the observer moving, the Doppler effect we get is a classical Doppler effect that we got with the classical wave theory. If we compare with the relativistic one, the relativistic one will have a gamma factor, okay, that we don't have. Okay, we can also analyze the amplitude of this is in frequency domain, the amplitude change, but in time domain the amplitude doesn't change. When you move the observer, it doesn't see the amplitude changing, which makes sense. You don't see if the observer moves, why will he see the amplitude increasing if it moves? Okay. This is for rotating observer point. I think I would pass this one, and accelerating observer. Now let's go to the moving source. So we still have. So now you see the red point here. The observer is not moving. It is the plane wave source that is moving. We don't see the plane wave source moving, but we will see the wave generated by this source. So you can see this one is propagating in this direction and the other one propagating on the other direction. So what happened to that one? The wavelength is smaller, so frequency is higher, and this one frequency went lower. It's Doppler effect. It's because the source is moving in this direction. Frequency lower, frequency higher. Okay, just a Doppler effect. And that's what we plot here for different V over C. So the black one is no motion, and the other one is when you move. So what you can observe here is the amplitude of the wave is not only the frequency that has changed, also the amplitude. And the amplitude actually go to infinite if the speed of propagation is equal to the speed of light. You can see it's increasing, and it's increasing with V over C. So I didn't like that. I thought this is not physical. So I change the model of the source by adding resistor. By adding resistor, you're making the source interacting with waves. It's not like an invisible or not interacting source. This one I consider to be more realistic. And if we use this, we add the resistor to the current source like this, and we move the source, you will get this result. So we still have the Doppler effect here and here, but when you look to the amplitude, the amplitude will stay always the same. The amplitude doesn't change, which makes more sense. Okay, when the plane wave source is moving, the amplitude don't change. But we had to add this. We had to change the model of the source. We have to make it a more realistic source. When you have an antenna is not something invisible. It has it is interacting with wave. When you send wave, it is diffracting, etc. So it has an effect. So you have to add this. It's more realistic. Actually, this idea of adding resistor came from my work I did in my PhD thesis, and you can do this analysis by yourself. It's not difficult. If you take a Fabry Pro made of two semi-reflective mirror, like this is a semi-reflective mirror, this is a semi-reflective mirror, and you send a plane wave, and you add all the waves. So you have this is reflection coefficient, this R, and transformation coefficient is T. They are complex numbers, so you have the first wave will be for T square. You add all of them like this, you will get this formula here. And at the resonance, if you have no loss, you can see, because T square, the absolute of t squared plus absolute of r squared equal 1, you will see that the maximum is 1. Okay, so at the resonance, if there is no loss, at the resonance you have 1. The wave is go through the Fabry-Perot cavity. Now, if you put the source in the middle, you can do exactly the same analysis we did here for the waves, and you get another formula here. But now you can see that the maximum is more than 1, and it can go to infinite. And this is where actually my supervisor, Professor Matoubi, proposed me to add the resistor to make the source more realistic. And if we do that, then I didn't put the formula here. We can show that the maximum is 1. Again, it's resolve the problem. The same thing we have here. So now let's go to Oliver Heaviside work in 1888. He did the analysis of a moving charge by using Maxwell's equations. So the same Maxwell equation that we are using and resolving numerically, but he did analytically. He moved a charge, which is a point charge. It's not that doesn't have dimension or mass, etc. When he moved that, he found that the electric field, as you can see, increased with V and become infinite when V equals C. But we show that using the same Maxwell equation, if we change the model of the source and we make it more realistic, it will not increase with the speed of motion of the source. So we think this one should be revisited, and if it is revisited, then there is no any problem when the moving source. At that time, there was discussion between Heaviside, Searle, and others that because of that, it was not possible to go higher than speed of light because the field was becoming infinite. Now, if you look to Einstein paper 1905, it is worse than that because he make it symmetrical. He got the same effect when the observer is moving, which is making totally no sense. You see here from this equation, it appears for an observer which moves with velocity c towards the source. So the observer is moving, not the source. The source should appear infinitely intense. He just makes it symmetrical. The problem, he make it symmetrical. The problem should not be there from the beginning, but he make it symmetrical and have that even for the observer. This is an image here I got from internet, and this one got it white. When the light, this is a light moving, if it moves in this direction or the direction, you can see the amplitude is the same, but just the frequency has changed, not the amplitude or the intensity. Here we can analyze also how the frequency is changing when the source is moving at different v over c, and what you can see is f prime over f equal 1 over 1 minus v over c. So in the other direction will be plus. If we compare with the relativistic formula, the relativistic formula has an inverse gamma factor. Okay. Now let's talk about the moving plane wave source. I didn't talk about that before. Here. Okay. You can see both this one and this one, they are propagating at the same speed. So the speed of the source didn't change the speed of propagation of the wave. Okay, that's we can see numerically. So this is an agreement with the postulate. If you read the postulate of Einstein paper on the electrodynamics of moving bodies, light is always propagated with a definite velocity velocity c, which is independent of the state of motion of the emitting body. So independent of the motion of the source. That is correct, but this is not when you take Voigt's variable as real, then he's doing something different. He make the speed of propagation independent of the motion of the observer. Now let's go to the first one with the moving observer. This one. So this is with Maxwell equation, okay? We just resolve Maxwell equation and we move the observer. How could we make, so when the observer is moving, you can see that the relative speed between the observer and the plane wave source is c plus v or c minus v? How could you make, with different speed of motion of the particle, how could you make the relative speed always to be c? It's totally nonsense. Here we show the line source moving, and you can see at different angle we can measure the wavelengths, and we can recognize again the Doppler effect at different angle. So at 0 degrees there is no Doppler effect here. At this angle here there is 1 plus v over c, and here we have 1 minus v over c. And we are the first one. I think this should have been done long time ago, but we are the first one to present a moving line source numerically using Maxwell equation. Okay. This is for accelerating plane wave source, rotating, etc. So this one I will pass this one. Okay, here we discovered something new. Okay, we have a metallic object which we consider has a perfect metal. We put E equals 0, so electric field equals 0 inside. This is a metal here, okay, and we can see the field inside. So when it is green, green means 0, there is no field. If the metal doesn't move, everything is reflected. But we observe when there is a motion, there is some wave going through the metallic structure. At the first time, we thought maybe there was a numerical problem, but then we thought that it could be physical, it could be real. And when we look to the magnetic field, actually there is a magnetic field inside the metal, and that's possible if we analyze the literature that was observed before, that metallic field can exist inside the metal. This is our theoretical analysis, and here this is analysis of how much wave is transferred. This is very small for when v is comparable to the speeds, normal speeds. It is very, very small. And here we want to see maybe we should change the boundary condition from the metal. So we were inspired by Lorentz field, but not using Lorentz transformation. And actually, this is how Lorentz did it. He just used the total time derivative. This is what I repeated here. And he used the fact that the divergence of the magnetic field here equals 0. And if we found that, he will get this expression. But we're not going to change to introduce E prime. We just say if E prime equals 0, what should be, instead of E equals 0, we're going to have E equal minus V cross B. So this one. So we tested this one. We tested this one. So when we test this one, the amplitude of reflection, the amplitude of the reflection coefficient is given by this. When we put this one, we get this one. And actually, this one is the same as what is obtained in special relativity. And this amplitude is greater than 1, increase. It can go to infinite here. And there is no field go to the other side if we use this boundary condition. But if we analyze energy, this one has a loss of energy. This one has an energy increase. But now if you go compare to experiment, there is a paper here in 1989 from a Russian scientist where they analyze fast-moving plasma, and they can see that the frequency is changing with the Doppler effect. It was correct with the formula, the 1 plus V over C, 1 minus V over C. However, they didn't find the amplitude increasing like this one. So no relativistic increase in the amplitude on reflection was observed. They found that the plasma was becoming transparent, which means the wave was going through. So we think it is more something like that, but maybe it could be different. If we test, for example, if we put equal minus 0.4 V cross B, we can have a conservation of energy. I think this has to be more investigated. Then we have moving scattering objects. If you have a moving reflector, as you see here, the Doppler effect will be f prime over f equal 1 plus v over c over 1 minus v over c. This is when the reflector moves in this direction. In the other direction, of course, it will be minus and plus here. And we can use also inclined partially reflective surface or semi-reflective mirror. We need that to analyze a Michelson-Morley interferometer. I would say here for the Doppler effect, f prime over f, this formula, again, it is in agreement with the wave theory of light, the classical wave theory of light. And for this formula, particle formula, not when it is inclined at a certain angle, for 0 degree, like this one, the formula here is the same with has special theory of relativity. So the Doppler effect is the same formula here. Like the gamma factor just cancelled. Then when we analyze the inclined pairs, we can also analyze. So we repeated the Bradley effect. We found the Bradley effect, and also we can analyze how the angle of reflection change, and we got the formulas here that it is not available in the literature. This one is when you have a plane wave source that is illuminating a metallic wire, and again you can see the Doppler effect 1 plus v over c over 1 minus v over c at this angle, and at 0 degree there is no Doppler effect, and at different angle we have the formula for different angle. Now, for example, for the reflector, there is no Doppler for this metallic wire. There is no Doppler effect at 0 degree. At 90 degree, sorry, at 90 degree here. But special theory of relativity predict a Doppler effect at this angle here. Okay, but we don't have that in simulation in FDTD. But it has never been measured directly. As it is said here, Jennison and Davis, 1974, 1975, they tried to measure the transverse Doppler effect from a rotating mirror, but they got null results. In this paper from Tim, he tried to measure accurately the Doppler shift. So he has a very advanced material he can measure a very small change in the frequency, but there was no the transverse Doppler effect. This one I will pass. I think this one is not important for this presentation. Also this one, I will pass it. And this is when we have a dielectric medium moving at different direction, different angle with different index of reflection of the medium. I will pass this one too, and I will go this one too. I will go to the radar application. Okay, next one. Okay, Doppler radar application. So here, what we did, we resolving Maxwell equation numerically, and we can introduce, for example, here a hat in action. This video we got, this is a professional or medical accurate video about a hat in action. And if we send a plane electromagnetic wave, and we analyze the reflected wave, we are the first one to get this radar cardiogram. So in black, you see here, numerically. If we analyze the literature, this is what they got in blue. The red one is ECG, so electrocardiogram, and the blue one is RCG, so radar cardiogram. So you can see what they got experimentally, the blue one. And there are different papers, not only this ones, who get this kind of curve experimentally, but we are the first one to get numerically. Why? Because we use Maxwell equation, we do resolve numerically, and we use it directly without using any transformation to resolve the problem of moving structures. And I think people they didn't think that it was possible because they thought that they have to do this transformation. Now we did the same thing for respiratory system in action here. And you see this, the red curve here. This is experiment, and we are the first one to get the same kind of curve numerically, so by simulation. We also work on doing experiment, and for example, we record the motion of a hand gesture. There is many applications with hand gesture to control with a radar system using hand gesture, and we can find we validated our work experimentally ourselves. Now I want to talk about the Michelson-Morley interferometer. So everybody know the principle. The principle, this is the interferometer, and we consider that we're moving through the light medium, the ether. So if we're moving through the medium, we should have a difference between this wave, this light wave going in this direction, and this one going in this direction. We should see a phase difference. Okay, this is what we see here between this time here and this time here. Between this time here and this time here, we should see a difference, and so we should see a shift in the phase between the two waves. We send one signal at one frequency, so it looks like a sine wave, and if there is a certain shift between the two, that will represent a different time here, and that will be able to detect the motion of the interferometer through the ether. Here I want to talk a little about what is a phase difference. So this is a blue one here and the green one. Between the two, there is about 90 phase difference, and between the blue one and the green here, about 180-degree phase difference. Now we have to think that a reflector, like what we see here, when we reflect a wave, it can change the phase of the wave. For example, if you use a perfect metal, you will introduce an 180-degree phase shift directly. If you use other materials, this can be the other value of the phase shift. And if you use a moving inclined mirror, then the phase of the reflection coefficient will change with angle of inclination. So that means this reflector here and this reflector, this reflector here and this one, they will introduce another phase shift, not necessarily due to the length of the propagation of the wave, of the light wave. It could be also introduce another phase shift. So that means the Michelson-Morley interferometer is not well designed when he introduced additional phase shift at the reflector. Here we try to replicate to see if Lorentz, so this formula that we see here were developed by Lorentz, this one and this one. So we want to see if we can replicate them numerically. So we analyze, we have the observer here, two observers moving, and we analyze in the longitudinal configuration and the transverse configuration, we analyze how this is the time delay we get. And this is a different time delays. So we found that the time delays was not actually, for the longitudinal, we got the same directly. And for the transversal one, I didn't show. Yeah, for the transversal one, we got a little more complex formula. But after that, we found that actually the two beams were not convergent; they were divergent. So we had to change a little the angle of the semi-reflector to make the two beams convergent. And when we do that, then we got the same as Lorentz, so the same formula. So it cannot be at 45 degrees; it has to be a little different for 45 degrees to get the same, to get the beams converging. And actually, it was interesting to see that this was analyzed by Michelson in his paper, not very, as accurately that what we do numerically, but he was able to analyze this effect and to see that this effect was small actually. So now we want to complete this work by see how the phase of the verification coefficient change with different mirror. But we have to analyze what frequency of the signal was using by Michelson and Morley, and what material was used for the semi-reflector. Another explanation of the result that he got is the electromagnetic field are moving. Then if the electromagnetic field are moving with Earth, then that will explain also the results. You will not need lens contraction for that. In Michelson-Gale and Pearson interferometer, one thing that is interesting in this interferometer, they are using the same path. So there is no bias about the reflector that they have with the previous interferometer. And also the effect is a first order effect. The effect is larger it's easier to measure experimentally. So the Sagnac effect, which is what so Sagnac wrote a paper to show that he can prove that the theory of relativity was not correct. He used something similar to what Michelson-Gale used after. They were inspired by Sagnac, and he was turning the interferometer with a certain velocity, and he showed that he was a French shift by doing so. And we can do that in FDTD with the moving observer and the moving source. So we did that with this kind of microstrip lines, and this one is this is microstrip, this is ring waveguide, and we can measure the time delays between the wave propagating in the two direction, and we got the same as Sagnac. And then we have to take into account if the moving medium has a certain dielectric constant or a certain refractive index n, we have to move the field. And by doing so, then we can also replicate the result that are being obtained experimentally here by Wang in 2004 with a moving fiber, and it shows that the Sagnac effect is independent of the dielectric material that is used. So the numerical analysis that we propose doesn't use Voigt-Lorentz transformation, as others have done in the literature. Our approach is more simple and give correct results. Here I want to talk about heaviside faster than light analysis. So is faster than light possible? So many scientists say that, like Tesla, claim that he have measured faster than light speed of particles. And in the literature, they say that it will invalidate the theory of relativity. In Lorentz work, if we consider that the Lorentz summation are just a tool and the speed of light, actually in his paper, he limits V lower than speed of light in the model, that theoretical model, not in physical reality. In the beginning of the 20th century, Wilhelm Wien was among well-known scientists who claimed that the speed of light cannot be exceeded based on heaviside analysis of the moving charge. So the energy becomes infinite when the charge is moving, and when it's moving at the speed of light. And he had strong influence on young scientists such as Einstein. But we have seen today that the moving charge, it will if we don't do anything in the Maxwell equation, we don't add interaction of this charge with the electromagnetic wave, it will go to infinite. The energy will go to infinite. But if you model differently, it will not go to infinite. And then there is no argument now to say that you cannot exceed the speed of light. And Heaviside actually said that he's not afraid of infinity. I'm not afraid of infinity. And he did analysis of a moving charge faster than the speed of light. So this is what we see here. And this is the angle that he analyzed. You see sinus theta equal V over U. V is the speed of light, and U is the speed of propagation of the charge. So we did that numerically. We move a line source faster than the speed of light. That's what you see here. So we just use Maxwell's equation and we move the source faster than the speed of light. And if we analyze the angle that we got, it's the same angle that Eberstein got, and the same as what we call the Ernest-Mach angle. So the same formula. Compton experiment. Compton is a very well-known experiment about, how you say here, the scattering of high-frequency photon after the interaction with charged particles, usually an electron. So we send a very X-rays to electrons and analyze the way the signals at different angle here. And he got this formula by using special theory of relativity and by using quantum theory. And experimentally, this is what they got at the 0 degree, 45 degree, etc. So we thought maybe we can replicate that with Maxwell's equation without using special theory of relativity or without using quantum theory. Let's consider, for example, here a line source moving with a certain speed, and we have a diffracting object here. This can represent a radiating charge, and this one a diffracting one, so a bound charge or bound atom. And if we do this simulation just using Maxwell's equation, we didn't introduce any new physical phenomena here, just moving the source, and we can see we can replicate the two peaks at different angle. We can analyze numerically by the Doppler, because of the Doppler effect. There is different frequency at different angle. So we can replicate the experiment, and we can get this formula here, V over C 1 minus cos theta, for the difference between the two peaks at different angles. And if we compare with the Compton formula, then the two can be made equal if we satisfy this equation. And that's interesting because this equation was used by Louis de Broglie. He called that the conservation of momentum for a moving electron. So for us, what we introduce is only V, so the speed of motion of the electron. So that means the speed of motion will be a function of mass and the Planck constant somehow. Then there is also another quantum experiment, the black body radiation. You can see here we were able to replicate for different temperature Planck's law. This is, for example, for one temperature, and this is for another temperature. Again, this is only with using Maxwell's equation. What we use a lot of sources with a random distribution of the frequencies. So source can be called oscillator or resonator if we want, electromagnetic source. And if we analyze the energy, we will get versus wavelengths or frequency, we will get the same as Planck's law. So if we compare, Planck got first he got this formula, and then he had to explain this formula, or this law that he got, and he explained it with the energy equal NHF. F is a frequency, H is a Planck constant. And that will be the energy of each oscillator. He considered he has Hertzian resonator inside the cavity. And this is what I show here. This is a Planck model, and this is our model. So in Planck, he considered that each resonator has energy N, HF. N can be 0, 1, etc. But this raises some question. This is an oscillator, for example, here. So what is the frequency of this resonator? Is F. It's not a defined one. F can be 0, can be infinite. So one oscillator doesn't have a defined frequency. And the other question is, if this is an oscillator resonating at one single frequency, for example, 1 Hertz, then how come this have an energy? An oscillator, so a sine wave doesn't have energy. If you integrate the energy for sine wave, it's infinite. In order to define energy, it has to be finite. And if you make it finite, then it doesn't have one frequency. It has a lot of frequencies, a combination of different sine waves. So it's not possible to define this oscillator oscillating at one frequency at the same time has energy. It doesn't have energy. We call that power signal, not energy signal. So like a pulse has energy but doesn't have power. A sine wave has power but doesn't have energy. So in our model, which is in alignment with classical physics or classical electromagnetism, we consider that each source has a frequency, f, okay, and the distribution of the frequency, we use what we call the Rayleigh distribution or Maxwell-Boltzmann distribution, but we apply that to the frequencies. And because of the interaction between the different waves, we got the same as Planck's law, as you can see here. So it's purely classical physics here. Okay, so this finish my presentation. So in conclusion, if we use the FDTD method for moving bodies without using Voigt's auxiliary variables, what people call Lorentz transformation, this gives meaningful results in different problems. There is no contradiction between classical physics, Newton, and Maxwell theory. When you take Maxwell theory and you have moving objects, the results you got are all in agreement with classical wave theory, so with classical physics. The utilization of DTD could be extended, we think it could be extended to the quantum phenomena. This is a list of papers we publish on the subject. So from 2023, 2025, I think this one will be in June, and now we are in the middle of the year. So it's about two years. Okay, so thank you very much. I think I took more time than I was expecting.
Well, thank you very much, Halim. And I've no objection to your running over slightly. I actually wasted a bit of time myself at the beginning. This is most comprehensive and all-embracing and actually quite fascinating. And I'm sure the audience feel the same way. You've covered so much information there, and it's actually complex and highly theoretical, but you've explained it, I think, in a way that most of us can gather that you've been able to replicate the experimental results that we have up to now using your analysis and the FDTD method. And obviously in the modern computer age, something that really wasn't available to the earlier experimenters that you referred to. This seems to be a very fruitful means of endeavor. I was particularly interested, just very, very briefly, in your concept of what are commonly called all these transformations, that they aren't really transformations, and it's a bit of a misnomer. And quite interested as well in the conception that maybe what all these mainstream scientists have been doing, and many of us have been criticizing and getting nowhere, perhaps looking at it a bit tangentially, have really been a blessing, because it has diverted many of the others to other perhaps work, and permitted you to engage in this analysis. So that's an interesting point. Actually, I might just say, from my own selfish point of view, this has been quite illuminating, because many of your ideas and concepts, I think, are in harmony with a lot of the ideas I have been engaged in for some time. And it's encouraged me, actually, because I've sort of intuitively felt that many of these mainstream ideas are wrong, and I've tried to give some reason for that. But you've given a very solid basis for that. So before handing it over to the questions, and we might go more directly into the green room, actually, because of the time limitation. But just maybe one point: have you looked at, or how does it fit into your FDTD FDTD system, the conception introduced by people like Hertz and so on of using a full convective derivative in the Maxwell equations rather than the simple time derivative.
I didn't understand well your question. You mean
okay? So it seems to me that you're getting the right results, by using the method, and you can use this sort of like tools of the Voigt systems and change the time without saying it's really time. But how does this fit in, or have you looked at how it might fit in with using a total derivative? So in other words, you use the
with a
plus the convective term.
But the problem, once you introduce the V in the equations, then you are limited yourself. How can you apply that to general motion? If you put V in the equations, if you see in my equation in FDTD, there is no V for resolving electromagnetic field. There is no change of the formula for electromagnetic fields. We move the object because the time FDTD is a time domain. So in the loop, we can move the objects. But if you change Maxwell's equation and introduce V inside, that means you are limited in the application. How can you use that for other motion? I think.
Okay. Okay.
You know what I mean? If you take Maxwell's equation, there is no motion. So there's only electric field is a function of magnetic field derivative with time and etc. But if you modify this equation and you introduce V, then you fixed with this V, and you cannot resolve that for more complex motion.
Okay. Well, thank you. So I've been trying to get a general sense of the questions. Because of the limited time, I'd like to give plenty of time for the discussion. And most of the questions are, to and fro's, which is fine. I mean, we have Jerry Mortensen is actually, as far as I can see, supporting a lot of your ideas. There's maybe one question here, a specific question from Cornelis. Perhaps I could put it up. I don't know if it can be done quickly, Halim. And I'm not quite sure what was talking about, because introducing a resistor. Could you go into more detail as to what your logic is for adding a resistor to the source? This is very significant, as in my view, the source is itself pattern of waves.
So I talk about that with the Fabry-Perot cavity. If you have a current sources inside and you analyze the waves, you will find that there is a transmission coefficient go high and can be infinite, and it makes no sense. And it's a real source cannot be without resistor. Actually, if you analyze what we call the power available from the source, and if you put R equal infinite, which is no resistor, then this source should not radiate at all. It is not a correct source, and that's why you can increase it, because it's a zero from the beginning. How can I say it more? If you consider just current sources, no resistor, you are saying that there is a source. If I send a wave to it, it will not reflect. So it doesn't exist, this kind of source. So firstly, it's a bad source. We can analyze the power, and we found that this source doesn't radiate from the beginning. And secondly, a source that doesn't interact with the waves themselves, it doesn't exist. I hope this responds to the question.
Okay, well, I think actually you're doing very well, because you've introduced a very complex subject, as I say, but you're one of the few people, sorry to say this, who has the ability to get to the nub of something and give a precise explanation without going into all the background details.
If I want to add something, this why is a question of heavy side work. every side is also using Maxwell equation, but he's doing is resolving analytically, and it is a point charge that is moving. So after there was interpretation, maybe this increasing is because the mass of the object is increasing, or the field is becoming more focused, and there is like what we call the AV side. I forgot the name. The ellipsoid. This kind of explanation that the field is really increasing. But if you use Maxwell equation, numerically, you will get the same result. But if you use another model for the source, still using Maxwell equation, you will see that the field is not increasing, and that's more in agreement with reality. There was never observation that moving source will increase the intensity of the source, like a proof that there is no conservation of energy in this specific experiment.
Okay. Now, the people in the green room, if any person would like to raise his hand, I can bring him in immediately. I see James Keane has been putting a few questions in there, and probably the best would be to discuss it. So I'll bring him in. Okay. Jim, as always, some precious ideas.
I enjoyed your presentation. In your finite differences time domain methodology, what was the finite difference for length in meters and time in seconds that you use?
Yeah. You talk about the space mesh and time step. You can make them very, very small. That's a nanosecond or picosecond. You can make it just.
Well, that was my question. What is very small in meters and seconds? Not very small. Could mean anything.
Yeah, you put them in lower than nanoseconds, picoseconds, nanoseconds, I think, something like that. And the dimensions.
Well, that's not very. In my software in binary mechanics, where I also do simulation, that's a very crude. I mean, nanoseconds. That's extremely crude.
Yeah, maybe no. You're right. Yeah, much smaller.
What value in meters do you use for distance?
You can make them. I don't have the value exact that we use there, but you can.
How would you write a program when you don't have the value? I'm questioning the whole enterprise.
Yeah. No,
if you can't tell me in meter and second values that you used in your simulation, well, I mean.
No, I cannot tell you.
Where are we now?
Value we use here because the simulation are done by the PhD student. The program
are done by who?
By my.
I mean, presumably student. These are variable. You have the program, and then you decide to run it with particular values.
You can.
Well, that's the question. What are those values?
Yeah, you can take a certain problem with certain dimension. Let's say an object. It is, for example, 2 centimeter. You will discretize this object, and for the space mesh, you will use it as function of the wavelengths that you're using. Usually, we use, for example, if the frequency is in terms of the wavelength is lambda, we use at least lambda smaller than lambda over 20. And for the time step, we have to be in agreement with the current limits. So you have to make it has to be smaller than a certain time step to avoid to have convergent results. But it's not how do we say?
So in other words,
when you make them small enough, they have no effect in the results. When the results converge, so I don't know why you specifically ask the question about the dimension, because it doesn't have an effect in the results.
Well, I would assume that the smaller the value for your as you called it, the mesh for space and time, the more accurate your results would
Yes,
be.
yes.
So I'm a little surprised to hear you say that it doesn't affect your results.
No, yeah, of course. You make it small enough, such as it will have no effect. If you make it, for example, you have a certain mesh, and you decrease the mesh, and the result change. That means you have to decrease again. But for a certain point, the result will not change. It will be small enough because, as I showed before, the finite difference is based on you have the error it will be a function of delta x square, for example, or delta t square. But
okay, so you gave the value of in the nanosecond range for your time mesh. Can you give a value where these results don't change for your space mesh?
Yeah, I
in meters.
I think it was even more smaller than that. I think it's picosecond or even smaller than picosecond. I don't have the
exact time. Sorry, length.
What's the length mesh?
Nanometers. Something
so
like
the
that.
length mesh we have to use is depending on the frequency of excitation. If the frequency of excitation has a certain wavelength, let's say lambda, the mesh should be smaller than lambda over 20. Smaller than that,
over 20.
It will not change the results.
Give me, I don't know what lambda is. What would be in meters? I mean, I'm just.
Yeah. Okay.
Should I not be surprised that you can't name a value in meters?
No, because we have
getting simulations that you routinely use.
Yeah. Let's say, for example, I'm working at. Let's say I work, for example, at. Okay, so if I'm not wrong, so it's 30 gigahertz. I think lambda is 1 centimeter. If I'm not wrong, yeah. So 30 gigahertz. So for example, I use a excitation of 30 gigahertz. Lambda is it's about 1 centimeter. If I have a certain object, for example, this one is about.
So your mesh is 1 centimeter?
No, it will be 1 centimeter divided by 20.
A 20th of a centimeter.
Yeah.
Well, that's huge. Oh, okay. Thank you.
At least. It depends on the.
We can obviously come back to this.
In other words, these are very gross measurements here.
If you'd like to pop in some of those parameters that Halim has talked about, and if you want to come back to us about any problems you have in the future, we can do that. Can we leave it at that for the moment, Jim?
I can add that the method we. Sorry, just fast. I can say that the FDTD method we are using exactly the same we are using for regular design of circuits, etc., microwave circuits, etc. So we just added motion inside it. So in terms of the numerical techniques, is proven, and there is no, problem in the tool itself.
Thank you. Thank you very much.
Thank you, Jim. Thank you. Now, I see in the green room chat. Yes. Oh, Harry is there. Danny put it kind of. I'll bring Danny back, but Harry is asking for the floor. So, Harry, please come in and make your points. Welcome. I can't hear you. You're muted, Harry. Your microphone must be muted. No. You'll have to unmute yourself, Harry. Your microphone.
There was another question by James. Observer moving with reference to what?
Where did you see that? Is this the general comments?
Private chat.
Oh, the private chat.
Okay. Can you explain the?
You've got to now, Harry.
Method that you're using, which is finite element method analysis. Can you explain that? This seems to be a problem.
Did you get that, Halim? He's breaking up a bit.
Yes,
I think he wants you to explain maybe the principle of the finite difference systems.
Also,
yes.
What is the Yi algorithm? What is the Yi?
So Yi is invented.
And what it explain.
Okay. I think I got the question.
Okay, Harry, we're going to deal one at a time. It's all breaking up. Yeah.
So the finite difference time domain method is used by many people. So the principle is using Maxwell equation in differential form. So you have to do a first order derivation of electric field component and magnetic field component with space and with time. Each of this differential, for example, delta E over delta X, you will resolve this by using finite difference, by using, for example, E at point. So you will have a mesh. You are going to mesh the space, and you will get the difference between the electric field between the 2 points of the small mesh divided by delta X. This will replace the delta E over delta X, for example. You do that also in time, and you do that for all of them. But when you do that, because there's an integration between the electric and magnetic field, you have to put them at a little different positions. You cannot put them all at the same position, the electric field components and magnetic field components. And Yi proposed an algorithm and the cell how to resolve the equation. But you can find this is a very known method. You can find more information about this technique.
Okay.
And I have some presentation.
Actually, Halim, Harry has left. I don't know if that means his system was cut off. But anyway, I thought we were more or less at the end. I'm having a few hands there. Denny, in particular, has put a number of points into the chat. So let me bring him up, and Denny, you can put your points directly to Halim.
Thank you. Yes, the finite method, it converges when you can no longer accurately compute how small the error is. And I use that quite a bit in the Runge cutoff, for example, integration. And if you say a time step of 1/100th of a second, and then you redo it with the 1/200th of a second, which would be half, then if you get this basically the same answer, there's no point in making the time step any smaller, because you're going to get the same answer every time.
Yes.
And so that even though I don't use the time domain like finite time domain like Halim, I believe it is, when I ever have to calculate anything that I can't get in closed form, then I have to use Runge cutoff method of integration of differential equations. And the rule is, as I say, is that if you think you've got an accurate answer with a certain time step, half that time step and then recompute. And if you get the same answer, there's no point in continuing any further. And of course, your answer will be accurate to the number of bits that your constant that you're putting in are good for. You can't get something from nothing. If you're computing your constants with 4-digit accuracy, and you want the 8-digit accuracy answer, you're just fooling yourself. And so although I don't use this method, I think it's very valid mathematically.
Yeah, thank you very much. Yeah, we check the accuracy and the convergence when we present the result. All the results we present, they have we check the accuracy and convergence.
And I think you've been doing parallel work in some sense, because Danny is basically a mathematician, and you know, he's been using these methods, I suppose, to solve differential equations. So you're basically
yeah. If Voigt has this tool, he will not have used this auxiliary variable. He would have used it to solve the question he had.
Okay. So can we leave it at that, Danny? Thank you very much for that. You just made another point that power considerations forbid instantaneous changes of energy. Of course, that's true as well.
Yeah, that's another thing. The power considerations, you can't go from zero energy to a finite energy without traveling between. That's what power is more basic than energy. And you can't, even if you flick a switch, there is a continuous, almost vertical in the graph, a continuous increase of energy. Almost vertical, but not quite. And so that point that Halim made too is valid.
Thank you.
Okay. Thank you very much for that point. So thanks, Danny. I'll move on now, if I may, because we're running out of time. I think maybe Cornelis wanted to come in. We don't really have time to go into much detail, Cornelis. If you want to come in still very, very briefly on one point, I'll bring you in. But please be very, very brief. We've just almost run out of time.
Okay. Thank you, Halim. It was a very good presentation. I worked with finite element analysis myself, and motor magnetic field analysis and design. And I think it's a real wonderful tool. I wish I understood it better, because I've plugged the values into it. I don't understand the mathematics behind it. I'd love to use it in concept of my own theory, but there again, I don't know. I don't have access to the thousands of dollars it would cost me to buy a proper package. At any rate, what you're using in the finite element analysis, you mentioned quite often that you don't have to use the Lorentz theory and transformation in that. But what I observe with finite element analysis or anything like that, you actually have a third frame that you're dealing with, which is the mesh itself.
Yes.
And so you don't need to transform, because your mesh is doing the transforming for you from one frame to the other, from the observer frame to the source frame. The other thing I observed and I mentioned is that with the resistance characteristic of the source, and it makes sense to me that the resistance characteristic of the source is there, because the source itself is an electromagnetic field that's self-contained within the structure of the matter. So that electromagnetic field is going to be affected just as much of moving through the mesh, if you will, as the wave itself is. So that I can see where the resistance is there. The resistance that caused the speed of light to be limited is also the resistance that caused the change in the shape of the source. But I just wanted to kind of have you explain that yourself, and so I appreciate that. Thank you.
Thank you very much. And by the way, may I just chip in a second, Halim? I mean, is there an essential difference that's worth noting between finite element, which Cornelis talked about, and finite difference?
I'm not expert on finite element. I think in terms of meshing is something similar, but I don't know all the details of finite element.
Okay, so your point again, Cornelis. I'm sorry, I probably diverted you a bit, because you were going on about your use of this in the motor industry and so on. So what point did you want to?
My main point was addressing the idea that you're actually using a third frame when you use a finite element analysis. You actually create a frame that is equivalent to like an ether or a background frame that you're doing all these wave transformations and comparisons. In the graphics, for instance, that show up, there is the background of the graphics itself that is used as a reference frame. So because you're not actually the observer looking at the source with no reference frame between you, you don't need to have a transformation equation to do that.
Yeah, if we take Maxwell's equation like they are and we resolve the FDTD, there is a background frame. You can move on that background frame and analyze the effect of the moving reference frame in that frame. So there is a ether frame there.
Yeah, so that's why we don't need the transformation, Lorentz transformations. You have a very simple flat background because you know where that background is, but in reality, we don't know where that background is. When we're the observer and we look at a source, it's all relative, those two items, and that's it.
Exactly. But,
so thank you. Appreciate it.
That seems so, Cornel. Thank you, because that actually concentrates our mind a bit on some of the essentials. Thank you very much for that contribution. Now, I do apologize for the rushed session and question and answer, and in particular the discussion with members of the Green Room. But in another sense, I think it's not to be totally regretted, because Halim has gone into so much information. We could easily have split this lecture into 2 sessions or more, and he's come. We may actually bring you back, But before maybe summarizing and giving some of my own crackpot ideas, I'd like to give you an opportunity of summarizing your own talk, and in the light of some of these points that have been raised, which perhaps we didn't have enough time to deal with today in great detail, you might want to address them, and you might want to propose how we might go forward, and how you yourself are going to go forward in this area. So I'll give you some moments yourself, without my interrupting you, to summarize, Halim.
Okay, thank you very much. So my idea is that Voigt, so what we call Lorentz transformation, is something invented by Voigt by using the wave equation, and they are auxiliary variables with no physical meanings, which are not needed. If Voigt has numerical techniques, he could have resolved the wave equation with a moving observer without doing a change of variable. When we know that, we can work with the Maxwell's equation and see what's happened when we have a moving observer, moving source, moving, diffracting objects. And when we do this analysis, we found that all the results are in agreement with classical wave theory. So there is no contradiction between Maxwell's equation and the classical physics or classical wave theory. If we want to be in agreement with all experiments, like the Michelson-Morley experiment, Michelson-Gay experiment, Sagnac effect, and stellar aberration, then we can walk within this approach without introducing length contraction, by considering that the field is moving with Earth, but not rotating with Earth. And then we can also extend the FDTD approach to quantum phenomena. We found that we can replicate, for example, the quantum experiment results. We can also replicate the blackbody radiation results by using Maxwell's equation. So we can introduce the Planck constant there, but in a different way. We don't have to quantize energy. It's only classical physics. I think that's all.
Well, thank you very much. I'm for once speechless, actually. But when I was first discussing with Halim the possibility of us giving us a presentation, consequential on the very significant comments he's been making on some of our talks, I did delve into some of the information available, and I know that he's given some references, but I think they were very hard to read and so on. And Cornelis has put a question here, which is the exact same question as I was asking. Is there something like a basic website that we can look at for your work? And I believe there is. And I think I found a lot of information there. Unfortunately, I haven't had an opportunity in the last week looking at it just before this lecture. But so I'll just bring you back a second, Halim. Isn't there a lot of information on a website you have that we could refer to?
So my papers, they are more technical paper, so maybe it's more for specialized people. I have some presentation on my YouTube channel for about the FDTD, so courses about the FDTD method. And also I show simulation. I put some or electromagnetic simulation. Also, I put them in my YouTube channel.
Yeah, it was a YouTube channel. That's right. I'm sorry it was some time since I looked at it, but I was quite impressed, and I had intended to look at it a few days ago, so it'd be fresh in my mind. So if people go into YouTube and put Halim Boutayeb, I suppose they would get it, wouldn't they?
Yes, exactly.
Yeah,
yes,
I think that's what I did. So okay, that's excellent.
But I will try to do new videos to explain, maybe for a wider audience, to explain my idea about the moving source and how we can revisit the heavy-side moving charge.
Well, if you're going to do that as a result of some of the questions today, we'll be tickled pink. It's delighted. But sorry, just answering Cornelis. There's no specific link, I think, Cornelis. But if you go into YouTube and just put Halim Boutayeb name, search, you'll get his channels, and he's going to put up. Okay, he's coming back. I don't know. Yeah. Well, okay. What's the matter, Cornelis?
Okay.
Oh, that's okay. Sorry.
I was just saying I've got it. Thank you, Ian.
No, thank you. You're very welcome. Thank you for raising it, Cornelis. Okay, so that's it. Thank you very much. So I'll basically just close now, and I'll maybe just come back for a moment. As I say, I'm rather speechless for once. So he's one person who's done that, and it's a very precise analytical method, and I have looked myself at finite difference methods of analysis. The finite element thing I did dabble in many years ago, but didn't go into very great detail in. But I'm impressed with that, and of course, the sine qua non is that these things concur with experiment. And we don't have to explain things away. Oh, it's not concurring, but that's because you're not taking this into account, or you're not taking that into account. But he's dealt with all the major aspects. I think anybody seriously looking at this subject needs to. I don't know how many elements you have in your talk, but there were maybe at least a score, maybe more, and you went through each of them in detail. So the recording of this, I would actually urge people to look at the full recording, maybe not skip through areas as we might do before, had we been at the lecture. But go through the lecture again and have a look at the YouTube channel. And I hope at a later stage we'll be able to address some of these aspects. Actually, I'm even guessing that maybe Harry Ricker's session tomorrow might have a brief resume of what we've done today, and put down some of your ideas, and we might even be able to persuade Halim to come back. I know he will continue participating in our talks from time to time, and I do look forward to his contributions, but I'm also looking forward to our talking to him and maybe asking him to deal with some specific areas in more detail. So on behalf of the CNPS, we are very much indebted to Halim for having gone to considerable trouble to produce this very comprehensive lecture to people, most of whom are not specialists in the area. I look forward certainly to pursuing it further. This is not the end; it's only the beginning. So I'd like to thank you all for your participation. I'd like to thank you all for your questions. I'd like to thank all the people in the green room. I'm sorry it was a bit short, but that's probably my fault in a way. I did make an error at the beginning. I wasted a bit of time, and I'm not sorry at all that Halim spent an hour and 10 minutes rather than an hour. He could have spent 2 hours or more. I'd like to thank him very, very much for having given us this lecture over a short period of time after he was introduced to us. I mean, I know he hasn't been around for years, and sometimes we need to get people involved very much. What's the NPS? I'm not going to give a lecture to them unless I know what they're about. But actually, I've only seen his questions coming up and his discussions in maybe the last number of months, and yet he was quite open to giving us a presentation, and I'm delighted he did that. So thank you very much today. I'll close the meeting now, and we look forward to progressing this and other related subjects further. Good day.